Hello folks, I've recently done a teardown and repair on this power supply, and if you recall I'd done one previously on this one about a year before. Just for coincidence and no other particular reason, I've actually, believe it or not, got yet another HP power supply. This time it is a different model, so actually they're all different models, so I figured because they're different models it would be worth just get the camera set up there. It will be worth doing a teardown and repair on this one as well, looking at the similarities of the electronics inside these, and hopefully solving the problem. One interesting thing about this is it's got quite an interesting fault on it, and let me just show you that first. So power up, it works perfectly. Output's off. We can turn the output on. I've got 2 meters set up here. One is on output A. One is on, one is on output 1, that's on output 1, that's on output 2. So we're on output 1, dial up to 5 volts, works absolutely like a charm. Go to output 2 and you notice that if I dial down to 0, that it's reading 0 volts and 0 amps. On output 2, however, it's reading 3.9 volts and 1.072 amps. Yet the output is set to 0. And what's interesting about this is actually, if you hear me, I'm going to dial this up 5 clicks, which should be 5 volts on this digit. And there we get the 5 volts, no problem at all. So what's happening is the power supply is working exactly as it's, I have also checked this with the current, so the output works exactly as we would expect, except for the readback is inaccurate on channel 2. And it's inaccurate in precise proportion. So if you go down to here, 3.9 volts or 3.91 volts is what we're reading. Dial it up to 5 volts. Subtract 5 from that, and you're 3.91 volts. So it's simply reading some kind of offset. That's quite. And what's curious about that fault is inside this power supply, the analog to digital converter circuit is used for both channels, so the 2 channels are isolated, and in this one, a lot like the 3631A, there's analog opto isolators which are isolating the sense and control voltages between the 2 power supplies and the main control board, which is all going to one chip, which is a 4051. So it's curious that although both channels are working perfectly, the readback is only failing on one channel and not both channels. So I thought we'd investigate that, have a look and see what's going on, and take it from there. Okay, so I haven't yet opened this. I've referred to the diagram, which I eventually got. I tried a few places online, but nobody seemed to have one. Anyway, I eventually found a schematic diagram for it. So having consulted the diagram, that's how I know what the internals look like broadly. And the electronics are very similar to the electronics in the other power supplies. The same A to D converter, same basic functional block diagrams, same basic components, same regulator designs. They're all very similar. So the whole series, the whole 36 series, are all based broadly on the same design. Anyway, next thing I'm going to go take this apart, and then I'll come back and we'll do our initial investigations. Okay, so there's the first look. Quick visual inspection, everything looks intact as I would expect. It's quite dusty, so I think that needs a bit of a clean up inside. It's been sitting around, obviously in use for a long time in a reasonably dusty environment. Quite fluffy dust, so I guess that's maybe indicative of previous home use. Okay, so this board here, having worked on a couple of these power supplies now, let me just zoom in here, because so to me this circuitry here, right here, looks very, very familiar. This looks like the analog to digital and digital to analog converter. One of these 16-pin devices is almost certainly going to be the input mux. which I'm talking about, so we should probably start metering around there. Same analog to digital, digital to analog converter. Quite interestingly, these power supply designs, they have an analog to digital converter that's actually an audio specified DAC. It's an AD1851. It's specified for audio work, but it obviously works in this power supply. That's what they use, and the way this works and controls multiple channels is this is muxed into a whole series of sample and hold circuits, analog sample and hold circuits, using these polypropylene caps to store the charge, and effectively it switches to each one in high, reasonably well, at a rate it multiplexes them in and keeps the charge on them. Anyway, so I guess the next thing to do is to power this up and meter it and see what we find. I'm just going to go and refer to the schematic, which I've actually got online. I'm going to hand draw a basic high-level block diagram, and particularly the pin numbers, just identify the various things we want to meter, and then I'll come back and talk through that. Okay, so I've just reviewed the schematic, and I've drawn this. Sorry about the really poor quality drawing, but it's really just a very high-level layout of the power supply. And in particular, and one thing I'd always advise when you're trying to fix something like this, so it's got multiple suppliers floating around each other in different ways, you really need to identify your ground points, the safe ground points, the ground points that you can make known good measurements from. Otherwise you can really find yourself in a sticky situation. And the other thing is, if you try to use two probes when you're measuring, you stand a much higher chance of causing damage by slipping. Or anyway, so what I've done is I've had a look at the schematic, and from that I've built a picture in my mind of what the power supply situations the power supply situation looks like inside. And I've just drawn this down a piece of paper. So this is kind of the mental image I've got in my mind, because as I said to you before, the same analog switch has inputs measuring both channels. Okay, so that's the first thing to note, and obviously the first thing, given the nature of the fault, the first thing I want to be able to do, we know that channel 1 works perfectly. So I want to set and we know channel 2 seems to read higher than it ought to. So my the first plan of attack will be to power it up, measure, set it to 5 volts on the. I'm not going to worry too much about the current, because I assume wherever we find the fault, once we fix that, the current readback will work. So I'm going to set the output of channel 1 to 5 volts, and I'm going to measure here and just make a note of what we get. Then I'm going to set channel 2 to 5 volts, make a note here, and see what we get. Now, depending on the outcome of that, will really indicate, this is a good checkpoint to decide whether the problem exists inside the power supply, or the power supply regulator circuitry, or whether it exists in the analog to digital converter circuitry. So let me just talk you through this, because there is something interesting about channel 2 that's different to channel 1. And it's to do with the way these power supplies are laid out. So in effect, the analog to digital converter circuitry runs at 5 volts, and there's op amps and so on, so they're running at a plus or minus 15 volt supply. So I've represented the control voltages here. This is the power supply for the control circuitry, including here, and what that means is 0 volts here is connected to pin 8 of this chip. Okay, that's ground, that's VSS. VSS. So obviously any measurements I want to make on the inputs of these chips, I really want to reference to this 0 volts. And it's interesting, and what I wanted to do in the power supply is find a good point where I can pick up my negative lead of my meter, so I don't have to probe around with it, so I only end up with the positive. So this is what the circuit's laid out, and quite very similar to the last power supply that I fixed, the last Agilent power supply I fixed. The control voltage 0 volts is actually strapped to the positive output of channel 1, so it's a direct connection to channel 1, which means I can pick up the negative for my meter to meter around here and get sensible results. I can pick up the negative, I can plug the negative or the common terminal of my meter, my multimeter, into the positive output of channel 1. Now, so the point I was making about the interesting thing, that there is a difference between channel 1 and channel 2. Unlike channel 1, which has a direct connection, because it's 0 referenced, it has a direct connection, so getting, there's nothing in the way. With channel 2, because the design of the power supply, channel 2 and channel 1 are isolated, which means you can put them in series or parallel to double up on the current or voltage as required in your test environment. So in order to do that, clearly you can't have two completely isolated power supply channels monitored by the same analog to digital multiplexer, input multiplexer. They have to be isolated, and inside this power supply, what HP have chosen to do in the design is use analog optocouplers. So they're coupling the second channel, monitoring VMON and the IMON, VMON2 and IMON2, through these linear compensated optocouplers. And I will take a copy of I'll take an image from the manual and put that section in the blog post so you can see that circuit. They're quite interesting circuits, and basically there's two LEDs inside and a phototransistor, and they compensate by providing negative feedback to the drive on the LED. That's how they work. It always surprises me how accurate they are, but they seem to be quite good. Anyway, so really the difference between channel 1, which works, and channel 2, which doesn't, this is common, so it's reasonable to assume, unless this chip is faulty, which I wouldn't say was likely in this circumstance, then it's reasonable to assume that everything here and back in to the power supply, all the analog to digital converter circuitry and all of the firmware and all the rest of it, it's reasonable to assume that probably all works as expected. So what I'm expecting to find when I meter this now is, and setting both channels to 5 volts on the output, is I suspect we'll get a different voltage here than we get here, where in theory they should be very close to each other. And so, in looking at that and knowing that the two power supply channels actually work perfectly, then the likely area of fault is going to be around these linear opto-isolators. So that's my assumption, and I've drawn that just by looking at the schematic, drawing that out and having a think about the fault and relating it back to the way this schematic looks. There is a snapshot of the actual schematic, and that's the 4051. And the reason why I've honed in on that, because as I said before, this is an obvious place to do our initial measurements, because we have to work out if it's up here or if it's down here. And as I say, the likelihood is we're going to find the fault around here. So that's the supply. Now what I've got from that is I've got the part number, I've got the component reference designator, which is U27 on here. I know the pin numbers for the VMON and IMON for channel 1s and channels 2, and I've written that information right here, so we can just hone in on that chip, which will be on this board, get ourselves ready to power this up with this floating around. You'll see that on the power supply, I've just taken a banana lead, I've plugged it into the positive output of channel 1. I plugged that into the meter, just to verify that and just to make sure that I've got that right, just putting the meter into continuity mode. I'm just going to go onto the VSS pin of the chip in question. So it's what we're interested in is U27, which is this chip here, and here is pin 1, and what I'm looking for is continuity between pin 8 and what I've plugged into. Now on the meter I've got continuity there, it's actually reading 15.2 ohms, and if I look at the schematic, there is actually a 14R7, a 14 ohm resistor in series with an inductor, which is E9, which is up here for some reason. I'm not quite sure what it's doing up here. E9 before it goes to ground. So that accounts for the 15 ohms. So we've definitely got a good measuring point, a good low impedance measuring point for the meter. So I'm just going to get this ready to power up by putting something under here to insulate it, and then I'll come back and we'll take some measurements, and I'll talk back what I'm finding. Okay, so I've just put a book. It's the user manual for that other supply that I fixed. I've just got it there just to insulate it. You obviously don't want it moving about. I'm going to power it up. I'm just going to set the output of both channels to 5 volts and just verify that I've got 5 volts coming on both outputs before we take a measure. So where are we? Display limit. 5 volts on channel 1. 5 volts on channel 2. Let's check what the meter's reading. turn the output on, that would help. So 5.063 on channel 1, as we can see there, and 5.059 on channel 2. That's great. So we can definitely see that there's the 5 volts is coming out on each output. So let me see if I can zoom in here a bit for what that will be. Okay, so the first thing I'm going to do, actually you need to see the meter. Let's just get this over here. Okay, so the first thing I'm going to do is just as a quick sanity check. Let's get a better angle on that. So yeah, as a quick sanity check, just to verify that my meter's ground is in ground. I'm just going to look at the VCC supply on the 4051 chip, which is pin 16, and just verify that it's got a 5 volt supply as you would expect, and there it is, 5.013. And I'm just going to check the 0 volt just to make sure that we've got 0, which we have, and the same chip on pin 7 we've got VEE, which I would expect on here to be a minus 5 volt supply. And there we've got it. So it's powered up correctly. It's powered up as we would expect. So now I'm going to take a look at pin 13. If you remember pin 13, to have a look at the voltage that I'm reading on there. And on there I'm reading, you can see on the meter, 0.798 or 798. Let's just make a note of that. And then I'm going to take a look again, same thing, but this time on pin 4, which should be, I'll just verify I've written that down correctly. Yeah, see. Now I'm glad I checked that. It's actually quite an easy mistake to make, but when you're measuring this, you notice here there's actually 2 numbers. There's the pin number, which is here, and then there's the channel number. And I'd incorrectly written down 4 and 5 for the second channel, so I could have metered that and spent an hour wondering why it was looking very strange. It's actually pin 1 and pin 5. It's always worth checking these things. Is that? Yeah, weirdly, pin 5 would have been okay. It's pin 1 and pin 5. So pin 5 is channel 5. Right, so having a look then on pin 1, I would expect to see what we just saw there. And what we're actually seeing is 1.389 volts. So that's going to go a long way to explaining why we're reading a higher voltage on the channel 2 than we are on channel 1. That also confirms what I thought, that the actual problem is around here almost certainly. Now the problem with that, I am pretty sure, the problem with that is this circuitry is actually down in the main board at the bottom of the power supply, and that unfortunately means I'm going to have to almost certainly, I will have a quick look, but it means I'm almost certainly going to have to strip the whole thing down and get the board out, as we did, as I did for the last power supply. So okay, so at least we know, and at least we've got a good place to start. Okay, I'll have a look now and see what's involved in stripping this down, or getting access to the electronics we need to measure, and I'll be right back. Okay, I've done a bit of studying of the circuit just before I take it out, and I've located some of the components, and to be honest with you, what I found has sort of thrown me a little bit, because this circuit here, this is the schematic, and it's definitely for the right model, because it's it's coming off it's a HP manual it's coming out of. All the parts are in the right places. I've done a sanity check. Remember we said that this is the output that drives the ADC, the chip that we measured earlier. And so with the meter connected to the ground, to the positive input for its common, I've just done a sanity check and verified that D1 here, which is actually pin 6 on U105, is at the same ground potential which it is. So that's just a sanity check, just to confirm that what I'm doing adds up. So what's thrown me? Well, I've located these resistors here, which are for the reference, for the purpose of finding those references so I can measure them. And according to this schematic, they're 1K resistors. In this power supply, and I'll come on to that in a second. In this power supply, actually, that resistor there is something like 334, which is about 330 K. And this resistor here is a 0 ohm resistor, so that looks like a mod that's deviated from the original design, or at least this schematic. And it's really odd that it's actually that far out, this being 1K on the schematic and that being 340K. I then thought, so that's the reference. So then I made an assumption that this was sort of a mirrored reference. So I went and checked this resistor to see if that was 1K, and that's 300K dead. So it's a slightly different value, and it's really strange. Anyway, I need to. Sorry, that was 300K. Yeah. So this was also a high value, much higher and different. So these values seem to be, they don't quite seem to be adding up to what's actually in reality on the schematic. Now, you could assume, well, maybe someone's been here fiddling about and messing with it, but actually, that's the second problem. Most of the resistors where we can get the measurement points from are all down here. That's all fantastic and great. The problem is the whole base of this has been sprayed after the components fitted with a thin coat of lacquer. So actually, trying to get a meter on, I'm having to put quite a lot of pressure to get the tip of the probe to get good connections to actually take measurements. So that's going to be a bit of a challenge, I don't think I'm going to be particularly successful at getting very reliable readings without doing a bit of upfront work. So I think what I'm going to do next is strip this out of its case. I was hoping I could kind of wing it a bit and find a quick way of fixing it, but that doesn't look like that's going to be the case. So I need to strip it out of its enclosure, same as I did on the last power supply, and get it spread out on the bench in a way that I can measure it and do things with it, make sure I can get to the top of the bottom of the board. And what I'll probably do, I'm going to try and find a clean way of, without destroying it, clearing the lacquer off the ends of some of the resistors, identifying the specific measuring points that I want to make. So I'll do all of that really before I continue. I think the prep work will be well worth it, because if I don't prep for this properly, you know, as I say, it's going to be difficult and it'll be time consuming, take a lot of time. So I'm going to go off and do that, and then I'll go off camera while I take it apart, and then I'll come back on camera and talk about the next steps. Okay, I've managed to strip it apart. It's actually quite easy. It took only about 5 minutes. It comes apart quite nicely and pretty much the same as the others. The board comes out in one go. I had a quick visual inspection, I had a quick look around, and you can see, you know, it's pretty crusty and dusty, and you know, it's sort of horrible. A lot of the dust is sort of like fluff, so it's been around. I don't know. There's even one of those. I don't know if you can see that. There's even one of those. Let me see if I can see. Yeah, one of those things that fly about. One of those seeds. That fly about in the summer in there, so it's pretty manky. I'm just going to go and clean that up. One thing I did observe, it's probably something in nothing, but and you probably can't see it, but one of those devices, TO220 devices, there, it just has a kind of green copper, you know, the copper sulfate colour on it. That would indicate a little bit of moisture. So I'm going to give this a clean up, and then give it a good visual inspection, and just make sure there's nothing obvious moisture-wise. These in that circuit that we're looking at, those opto-isolators are all around here. So this is the circuitry here that we've got to get to measure. And again, just looking at it at angle in the light, it looks like the entire board, components included, are also sprayed in this lacquer. So that's going to be interesting to get measurements and stuff from. Anyway, we'll see how we go. So I'm going to go off and clean this, get the hoover out, and just generally clean this up so I don't have to get dust and crap all over my hands. Okay, I'll be back soon. Now, one other thing I thought I'd point out on this power supply, it seems to be particular to this specific model, because it certainly wasn't the case on the other two power supplies that I've repaired, is the AC voltage selector. If you look on the back of the case, it would appear when you look at it that there's no voltage selector on here. and there's a tick mark saying that it's 230 volts on this sticker, which looks like it's stuck on at the factory, so it's factory set. So you might take from that actually it's not, it won't work in say the US or any country where there's a need for a lower voltage, 100, 115. But actually inside the power supply, one of the things I really don't like about these power supplies, the way HP do this, is that the mains is brought in here. So off the main IDC connector at the back of the power supply, rear panel, the mains is brought into this point here. This is the switch, which is a hard switch. That's actually a good thing. And then it goes into these caps, and these actually two switches. So these two switches here, you can see on the board, you can actually set the voltage to the three supported voltage, which is 100, 115, 230 volts. So this is set for 230 volts, and then this is the connection to the transformer, the primary side of the transformer. Now the reason why I say I don't like this is I know it's convenient for production and so on, but it's, you know, if you're in the back here measuring, you know, the mains is live here. You can see that they've got, you know, good decent sized insulation. You can see right through the layer of the boards there. There's absolutely no copper there. So you know it's sort of done reasonably well. This is the, I'm taking this to be earth actually, is it? Just, yeah, this looks like to be mains earth here. But you know, when you're working on this, you can end up, you know, you can electrocute yourself. You can do yourself a lot of damage. So I normally, well, certainly on the other two power supplies, I've tended to connect the mains up separate and off of that board, just so I'd save myself sort of, you know, it means I can move the board around without too much worry of getting electrocuted. On here, I'm going to have to work out what the windings are, and I'll connect the mains directly to here, so I don't have to put mains on this. But I just thought I'd point that out because it might be useful to anyone if you're looking at one of these power supplies and it's set to the wrong voltage. It looks like you can set the voltage inside on those two switches. Okay, just a quick word on prepping to work on something like this. You know, you really, well, I certainly in this case, I need to be able to measure and probe around here. I need to be able to have a look under here and measure and probe under here. And you need to be doing that, you know, and be safe and make sure that you don't damage the thing. Now, one of the limitations here, having taken the transformer, just sit that there. Obviously, I've got some restrictions with the cables here, but that's okay. That's workable. There's a set of wires coming from the back of the transformer which need to go to this board. There's another set of wires here which need to make it over here. Yeah, obviously, you know, 6 inches too short. And these SpectraStrip ribbon cables are actually really too short. So that one, I've got that one in there. I thought that would be workable, but this one needs to go in here and make it over here, and now all of a sudden, you know, it's all getting difficult. So I think what I'm going to do, just to make it easier to work on, and this is always good practice, it doesn't take much effort, is get prepared to work on this properly. So I'm going to make a couple of cables. I'm going to make longer cables so I can actually lay this board somewhere out of the way, down over here or somewhere. So I need to make replace a longer one of these and a longer one of these here. I also need to make an extension for this. This is a standard 6-pin 0.1 inch pitch, so that's easy enough to find something or work something up. So that's the right thing to do. I'll go and do that now, and then I'll come back and show you what that looks like. Okay, so the first measurement I'm going to take, if I remember back at this diagram, this is the control side of the circuit. So this is the voltage that's coming out. It's the channel 2 voltage monitor signal. So it's a signal that's being driven into the board over here, into the analog to digital converter. So the first thing I wanted to do was just make sure that this side of that, so this side of that opto-isolator, which is this part here, this circuitry here, has a -10 volt reference on here. Now, in order to do that, you really want to make sure that you're measuring the right things, because it can get very confusing very quickly. So D1 here, I'm taking to be the ground or the 0 volt point for this line here. So if I can, if you remember, this is the side that's connected directly to the analog circuitry, and if you remember in the previous diagram, I'd explained that that the 0 volt line for the control circuitry was actually anchored to the positive output of channel 1. So I've got the meter as common pin connected to that. But what I'm going to do, I want to confirm that 100%. So it's not powered up at the moment. So I know my meter is grounded here. That's the thinking, and that goes to pin 5 of U105. So the simple way to check that, give myself a sanity check, is just get into continuity mode and go on to pin 105. Pin 5 right here of U105 to make sure that I've got continuity. So this is U105 down here. 1, 2, 3, 4. Okay, and that's exactly what I'd expect to find. Okay, so I've got ground here. What that tells me is I know I've got a good ground point here. So next thing I want to do is go and verify that if I can locate resistor 338 here, I want to verify that that minus 10 volt bias voltage is actually present. So to do that, we need to power it up into volts. And resistor 338 is here. Okay, so I'm not sure if you can see that here. Let's give it a go. So resistor 338 is right here, and I'm just going to check on there. I've got 0 volts there. I've got exactly minus 10 volts there, and you can see that right there. Okay, so looking at that circuit there, that's got minus 10 volts. We know that the circuit, if you recall from the fault, we know the circuit basically works. We know that as we wind the output voltage up, the voltage here rises because we see it on the meter, and we know it also rises in direct proportion. So if we've got a minus 10 volts here, we can assume the rest of the circuit, from a DC conditions point of view at least, is working. So I would say everything from here, pin 6 and pin 5 of this optocoupler, and everything from here seems to be working. By the way, when I checked for the ground, I was saying pin 5 of U105. I was actually on pin 6 of pin 6 of U116, which is the opto isolator. It's a bigger component, it's easier to spot. So sorry about that. That was just my mistake. So from what I can see, that seems to be that part's working. So the next thing to do then is to have a look and check for this bias voltage here. Now, one thing I wanted to point out, which is very, very strange, is I'm looking at the schematic here, and this is definitely the right schematic for the model. R338, it's indicated here to be 1 kilo ohm, 1K ohm. I don't know if you saw when I zoomed in, but actually R338, let's just do that. And this has never been touched or modded, so this is as it comes out of the factory. R338 there is actually 220k, 2 and 5 zeros. So that's very strange that the schematic, I've never seen a schematic be that far out before. It's very clearly here marked as 1k. Now the important thing there, given this is a reference and given this is biasing, you notice here that there's 2 1k resistors. I would have thought this would need to be there we go. This would need to be a similar sort of value. And in fact on our 339, which is somewhere, is it our R349 and 350, which are shown on the schematic diagram here as 1K and 1K. R349. Sorry, let me just tilt the camera. So what happens when you try and work a tripod from the front of the tripod? So you can see R349 there is also 220k, and R350 is linked out at 0 ohms. So in order to measure that, what we need to do is establish a verifiable ground point on this circuitry here. This will be sorry, this will be A2 here. So on this circuit, this will be A2. So I need to go and find that. I suspect that's the positive output of the channel 2, but we can just go check that now. So again, on U116, which is the optocoupler, we can verify that easily enough. Just zoom back out here. So the way I'm going to do that is I've just turned the power off. Go back into continuity mode. I'm going to go into the positive output of channel 2, and then I am going to just check. I can either go to pin 2 of this IC or pin 3 of U115. So I'll go to pin 3 of U115 because that's where I'm centering my tests around. Yeah. Okay, so that's clear. So I've just got a verifiable good ground point there. Now as I say, that's why preparation is so important. If you prepare and so you have a good understanding of the circuit, you'll often you'll be able to make pretty good guesses about what's what, and you won't have to trace things through and hunt the circuit diagram and so on to find stuff. So the next thing to do now now we've got a verifiable ground, back onto volts again, is I want to check this this minus 10 volt reference here, and just to see what we've got. Again, it should be minus 10 volts, and it should be on one side of R349. I don't know. Yeah, so it should be somewhere here. So again, power on. We're looking at R349. I won't bother zooming in this time. I think you get the idea. I probably figured out I can actually find the right component, so that's good. So R349 on one side of it. I'm actually on there now. I've got 0 volts. On the other side of it, minus 13.84. Okay, so that's interesting. So if we think about the fault is showing us that if you remember when we dial the output voltage up, let's just have a look at that for a second. Let's get the display limit here. Wind the output. Sorry, let's get onto channel 2. Wind the output up to 5 volts. Turn the output on, and we're getting 8.93 volts instead of 5 volts. So we're 3.93 volts above where we should do in the readback, and probably not coincidentally, if we're reading this reference voltage, which should be minus 10, we're reading 13.86. So it's very close to the 3.93 overshoot we've got on the voltage. So pretty strong indicator that the issue with this power supply is that reference voltage is meant to be precisely 10 volts, and it's currently 13.8 volts. So what I need to do now is consult the schematic diagram. Unfortunately, it's on my computer, so I can't show it here. And then I'll locate the relevant bits of the power supply circuitry, and I'll print them out, and then I'll come back and we'll take some more measurements. Okay, see you in a minute. Okay, so I've repositioned the camera. This is the relevant part of the schematic diagram. This is part of the power supply. It's on the main board here again, which is really useful. So there's nothing really sophisticated here. There's a couple of LM317s. This is generating a plus or minus bias supply, and the LM317s are generating a plus or minus 16.2 volts output. From that, it's feeding into this voltage reference chip, which is an LT1021, and that should be generating a plus 5 volt reference. If you see right here, and then we're feeding that plus 5 volt reference into a potential divider here, into an op amp. It's one part of a TLO74, and we've got the resistor values here. This is 17.4k. This is about 10. Not sure what that says. Hold on a second. 100k. And this is then generating a minus 10 volt reference, so that's got a gain of 2 somehow. Oh, sorry, 100k and 17.4k. Yeah, I don't quite understand that. That's it's definitely 100k. I'm going to verify those resistors, because that seems odd. Expecting to have a gain of 2 there, unless there's something odd about the way the JFET input of that op-amp works. But anyway, so that's what we're expecting. That's simple. That's a simple buffer, and it's generating from a positive 5 volts. It's generating a negative 10 volt supply. Oh, that'll probably explain why. Yeah. Anyway, so let's just check those DC conditions around there and just see what we get. The first thing to check for is on pin 6 of U106, which is this here. I'm just going to check that output. That'll be, you know, I can check this one, but I'll just go check here first, and if there's a problem I can work backwards. So I start at this midpoint here. So pin 6 of U106, you can see the meter there, and I would expect to see, if this was working, we should see 5 volts there or thereabouts. Okay, so we're getting 4.99 volts. So that tells me that that voltage reference that works well. So assuming that there's not a weird load condition here, the problem, I guess, must be around here. So what we need to go and do is locate this component, check on pin 14 and verify we've got this weird voltage, and then try and understand what's wrong with this circuit. Okay, so that is U118 and it's pin 14. So U118 on this board is this chip here, and I'm just going to get on pin 14. This is pin 1, so the opposite of pin 1 there, and there we've got our minus 13.87 volts, which is clearly wrong. So let's have a look at these two resistors here. So this is R136, which is 100k, and this is R148, which is 17.8k. So R36. R136. I'd expect it to be around here somewhere. Okay, I need to get closer, so let me just move the camera for a second. Okay, so so looking at this this power supply up close again, you know, this schematic. I'm not quite sure what's going on with this schematic, but you know, clearly it's showing here that R136 is 100k, and it's showing R148 as being 17.8k. Well, that's, you know, if you know, my very rudimentary understanding of how op-amp works, if we're trying to get a gain of you know, even minus 0.2, where it's just negative, it's an inverting input rather than a positive input, so that this will invert. You know, to derive 10 volts from 5 volts, you know, from 10 volts from here, from the 5 volt supply, hit the reference here, this circuit has to have a gain of 2. So, you know, in order to get a gain of 2, this resistance really needs to be double the value of this resistance. So if that's 100k, that ought to be 200k, not 17.8k as it's shown here. It's very odd that this schematic is so wrong. That's, you know, I've only looked at 2 parts of the circuit, and I found resistor values that are wrong in both cases. So I can only assume that when this schematic was produced, there was some, I don't know, bill of materials sequencing error or something, or maybe it's very, very strange. But anyway, let's just have a look here, because here are the components. So R148, which is this one here, as you can see, is 2002. So that is that's 20k. Let me just make sure I've got that right. 200 and 2 zeros. Yeah, that's 20k there. And then R136 is 1002, so that's 10k. So this schematic is wrong, and that would add up. R136 is 10k on the schematic. Let me just, yeah. Sorry about that. R136 is 10k on the actual. It's 100k here, but it's actually 10k on the circuit. And R148 is shown as 17k here, and it's actually 20k on the circuit. So we need to verify that that behaviour there. So now we know what the actual values are. Again, let's have a look and see what we get. So on what I'm expecting on pin 13 of the negative input is well, what I'm expecting on, let's have a look here on pin 13. What are we getting? Let's make some assumptions. So we're getting exactly 5 volts on pin 13. Okay, that's interesting. So if you look at this circuit diagram here, again, this is 5 volts. We're getting 5 volts here on this pin. Okay, and we're getting minus 14 or minus 13 volts here on this pin. So the only possible explanation for that is that resistor R148 has to be open circuit. Either that or this chip's faulty. But if this chip had a fault, it's very hard to see how it would hold this. You know, this is, you know, we've already established this is 10K. So any current draw here, you know, it would be highly unlikely it will balance it to exactly the 5 volts that it's seeing on this side. So really the only explanation is this resistor right here is open circuit. So let's just double check that, make sure that's the case, and then as long as I've got one of those resistors lying about or something similar, then we should be able to repair it. Okay, let me just power this down. Excuse me. I'll just grab a second meter here, just because it's conveniently set up. Put that one out of the way. Okay, so if the diagnosis is correct, then just a reminder, we're actually, sorry, wrong diagram. We're actually saying that R148 we're expecting to be open circuit and not reading the 20K that it should be reading. And it's got 64K. That's kind of what I'm reading. Just because it's in circuit, you don't know what other effects are around. It's just so 2002, yeah. So R148 looks like it looks like it's open circuit. What I'm going to do is I'll quickly desolder that, take it out, and we can measure it standing alone and make sure that is the case. Okay, I'll turn the camera off for now while I desolder it, and I'll come back. Okay, so I've just removed that resistor. Here it is. Can't really get focus on it. Give the camera something close to focus on. And yes, it's a 20K resistor. Marked 2002, and it's open circuit. So it looks like the fault for this power supply is simply one little resistor that probably costs less than a cent or a penny, and that's the fault. And I have to say, it's really quite unusual to see a resistor in a circuit like this, where really there's negligible current here. You know, if this is 10K and this is 20K, this is the resistor that's at fault. You know, there's really nothing on here this resistor is in no way sort of being overpowered or overrun. So it's unusual for a resistor to fail in that way. There doesn't appear to be any heat damage, there's no board damage, there doesn't look like there's any stress, any water damage or anything else. So very, very unusual to see a resistor, an SMD chip resistor fail like that, but it does happen, I guess. I don't know, I might take a look at this under a microscope and just see if there's any physical break or crack. As there may well be. If there is, I'll post a photograph up. But as it is now, that looks like the fault. Now the only problem I'm going to have, I know this because it's a gain, setting gain on an op amp. It's deriving a reference voltage. Those resistors have to be reasonably near tolerance, and they need to have a reasonable temperature coefficient as well. And I have fairly limited resistors to hand. I've got these ones, and these are all the ones that are actually good for, these are the only ones I've got that are good for that precision, that temperature precision, and so on. So I need a gain of 2. So I need 2 values, one half the other value, and I don't have that. Probably the best I can do is let me see, put either put 2 12Ks in parallel to get 6K and then a 3K, or put 2 3Ks in series to get 6K and a 12K, which is probably what I'll do. It's not ideal, because when you put two SMD resistors in series, you have to stand them up like you're stacking the cards, like a pyramid. So it's a little bit awkward, but I'd rather do that than sit and wait for components to come. It'll be easy enough to do. So I'm going to go and do that. Back to the circuit diagram again. You know, it doesn't. Although I was going to say, you know, is it a bad thing putting the wrong value resistors in? For this power supply, I'm going to say no, because HP don't seem to be able to do it themselves, or they certainly don't seem to be able to label them properly. You know, I'm being slightly flippant there, but you know, this is a really simple circuit to understand. This just needs a gain of 2, so that resistor has to be twice that resistance value, and you just don't. You want to do it. You want enough. You don't want those resistor values too high, because you've got the potential of inducing noise from circuitry around it here. So you want this to be relatively low impedance, but you don't want it to be so low that this op amp and this voltage reference are having to deliver too much current. So somewhere in the few to, you know, maybe say 2 or 3 to 50K range will be perfectly adequate in here without any problems at all. So I'm very comfortable picking a couple of values. So I'm going to go and do that, solder those in, and then we'll just do a quick final test and make sure that's resolved the problem. Okay, I'll be back in a minute. Okay, I've installed the resistors there. You can see this one here. I've stacked like stacking 2 playing cards, soldered it at the top, soldered it onto each pad. Relatively easy to do with 2 resistors. I ended up going with 2 3K resistors in series. Where are we? 2 3K. Let's just get this in focus. Sorry. Yeah, two 3K resistors in series in R148 and 1 3K resistor here. That's quite, you know, why did I choose 3K? No other reason than I had a lot more of those than I had of the 12Ks. So I just figured I'd use those. As I say, 3K, you know, the impedance here across 20 volts is going to be very low current still, so there shouldn't be any issue at all. Anyway, we'll just check it. I will actually, yeah, we'll just check the output now. Make sure it does what it's meant to do. Let's get ourselves set up here. Go to output 2, set the display limit, wind that up to 5 volts. Go back to monitored output, switch it on. There we go. 5 volts on the output. 5 volts being read back. That's a good fix. All right. So the only thing I need to do, I am just going to go and do a quick calculation on the current through that circuit, just because you know, we got plus 5 volts here, minus 10 volts here, so that's 15 volts effectively across 9K. Doesn't sound like very much at all, but I'll just make sure that's okay. Make sure that I'm not putting anything outside of spec. But other than that, that's a good fix. So I'm going to go and check that. Assuming that's okay, I'll put it back together, and then we can do a final test and wrap up. Okay, just before I put this together, when I was searching for the schematic diagram, I posted up to the EEV blog forum and asking for the schematic, and I got a fair few responses, so I was very grateful for all of those people that responded, and someone sent me a link to the schematic. But someone on there also pointed out that there was an engineering note for these power supplies, and it was relating to these capacitors. They're known to have known cold solder joints. Now, what the recommendation is actually just to resolder them, just to, when you've got it apart, just to make sure. Now, I have had a look at these under the microscope, and they actually look fine. But I'm gonna give them a solder anyway, just to make sure that that they're okay. Now, the one problem with soldering these is that there's very large tracks, because obviously this is part of the high current circuitry. So you need quite a high wattage soldering, and they recommend 100 watts. I haven't got that. Unfortunately, I've only got a 40-watt Weller soldering iron, but this tends to be pretty good for doing this sort of work. So I'm gonna resolder those just as a precaution while I've got the power supply apart, just to make sure that that there's no issues with them. Okay, I thought I'd point that out in case anyone else gets to see this video and is in need of repairing these. If you haven't found that engineering note, just make a point of checking those caps and making sure that that they're correctly and properly soldered. Okay, so I've put everything together now. I've given the power supply a clean up and just generally tied up. There was a little dent in the top of the top of the outer cover, which I've just straightened out as well using a vise and a couple of bits of wood. So it's all ready to go. I'm just going to give it final test. I don't think, given the nature of the fault, that it'll need recalibrating. So I'm going to assume the calibration's okay. All I'm going to just do is just test for getting the right voltage and make sure it can drive a load. So I'm just going to use a halogen bulb here. I'm just going to verify the output. So let's just make sure that it powers up. We'll check output 1. Okay, so turn the output up, on, wind it up to 5 volts. So there we go, we get 5 volts on the meter, 5.061. So it probably does need calibrating. Actually, that's what it was like before we done anything. But so it's a little bit out. So that's channel 1 working, no problem at all. Let's go to channel 2. Same drill, up to 5 volts, no problem at all. 5 volts set here, 5 volts in the output, about 1.85 amps on this lamp, which take that up to 8 volts is the max. Let's just put that on the higher output, high voltage. Okay, we've hit the current limit. That's great. All right, so that's working as far as I'm concerned. Happy with that. That's fantastic. You'll be pleased to know I've now run out of broken HP supplies, so that's my lot. I shan't be doing any more teardown and repairs on HP supplies because I've exhausted my stock of broken ones. So if you enjoyed the video and found the repair interesting, please give it a thumbs up, and thanks very much for watching.